In this video, we're going to make a custom PCB on the Sienci Labs Sienci Mill One CNC router. I'm going to show you the process that I went through to make this. If you want, you can follow along with your own PCB designs, but I'm also going to show you what mistakes I made, how you can learn from them, and what I would do differently next time. Now, first of all, why do you even want to mill a PCB? We have proto PCBs like this or strip boards that you can just solder your stuff to, right? But the thing is, these are practical up to a certain size, but as soon as you have to make more than just a handful of connections, or you need to make a second revision of your design, it's just a huge pain to solder everything up again. So having a PCB like this, is gonna work. You don't have to worry about a breadboard failing or anything, and you can use pretty much any component on your custom PCB. Now, the process of making a PCB isn't actually all that hard once you figure out all the steps that you need, and that's exactly what I'm going to show you in this video. We're going to be doing isolation routing, which means we take a raw copper-clad PCB like this, and then we mill out all the areas that we don't need in copper and create isolation tracks between all the different copper areas on the bottom here. For this, I'm going to be using the Sienci Labs Sienci Mill One CNC router. Sorry about the name, that has got to be the worst product name ever. I mean, you know how I joke about Slicer, Slick 3R, that entire naming thing, but calling a product actually CNC, where it's I'm gonna pop this up on screen. Sienci Labs, the Sienci Mill One, CNC router, like, God, it just makes talking about these things impossible. So if further down this video you get confused what CNC I'm actually talking about, well, sorry, nothing I can do. So for this PCB, I already kind of know what my design should look like. I have the components that need to fit on it. I've prototyped this on one of these proto PCBs, so I know my circuit is gonna work, and I've already got it all laid out in Eagle. So that's where we're gonna start from. So like most of my other electronics projects that require some sort of schematic or PCB, this started out in Eagle. This uses some custom cells for the boards that I'm gonna use, but of course you don't have to use Eagle. There are plenty of other options out there. You can use open source tools or more professional options. They will all get you the same result. And what we actually need is, of course, first of all, for the schematic to be accurate, and then we can switch over to the board, and you can see this is already all routed out. What you're not seeing right now is the ground plane that just fills in all these empty areas so that those don't get removed, but we can add that in real quick here. And yeah, this is the board that we're gonna mill. Now, if you're using the auto router or are drawing the traces yourself, you should definitely check out the DRC and just go through the clearance sections up here. These will determine how much space Eagle thinks is okay to leave between these traces, just to make sure that there are no shorts between these individual tracks. And you can also set the sizes for your minimum width of trace. I started with a 0.4 millimeter size. That is just something I can relate to, but usually you do these in mil, which I believe is 1/1000th of an inch. But I don't know, PCB and electronics are weird like that, where everything is still based on inches. But yeah, for a routed PCB like this, I would at least recommend increasing the trace width to something that you know is going to remain after the end mill or engraver bit or whatever you're going to use does its job. If you go too thin here, these traces will just disappear because a mill is not always 100% accurate. But for now, these are my starting values. I'm sure it's going to be a bit too tight, but well, live and learn, right? Now, I'm not going to go into all the details on how to do electronics design. That would be the topic for many, many other videos. But basically what we're going to need are the Gerber files for this board, and we can generate these pretty easily by going to the CAM processor, going to bottom copper, and that's just going to select the entire underside of the board. We need to go to advanced, mirror it horizontally because we're going to be milling it from the bottom, and the details for everything else are fine. So we go to export file, choose a folder, and hit select folder. Yes, replace. So we just exported all the copper traces and ground pads. Next up, we need a drill file. So we go up here to drill Epsilon, and that's the preview of all the holes it's going to drill. Again, double check that this is actually aligned the correct way. Down here, you can see this is horizontally mirrored. The Epsilon is not mirrored yet, so make sure that is enabled. And same thing, export, choose the same folder, select overwrite yes, because of course I've done this before. And lastly, what you can also do is to output the profile. That is basically this outer edge where your board is going to get milled out. And same thing, make sure it's mirrored. You don't really see a difference up here. It still looks the same because it's symmetrical. But the thing is, the 0 point is down here now. If you didn't have it mirrored, it would be down here. And of course, the Gerber files for the copper and the drill files would be on this left plane. So the routing path would cut out an entirely different section of the board. Okay, and that's all the files exported that we need from Eagle. Okay, so now we have the equivalent of an STL file for 3D printing. Those Gerber files are basically the blueprints for what we want to machine. Now we still need to turn those files into G-code that our machines understand, and that is done in FlatCAM. At least I use FlatCAM for this. There are plenty of other alternatives out there, but I found FlatCAM to be, well, the most usable, I guess. Now because Eagle is kind of weird in the way that it exports files, we need to set FlatCAM to understand the way that Eagle does things. So the first thing you should do before you open up anything is to go down here to the shell. If that is not open, you can open it up here with the command line and type in set_sys space epsilon underscore zeros, then uppercase T. There we go. So now FlatCAM is going to import the drill files correctly. If you don't do that, it's going to look all weird and messed up. So now we can go up here to File, Open Gerber, copper bottom. If you've not exported anything before, this directory is not going to be as messy, but you want the copper bottom first. And just a quick check to make sure this is opened correctly. We can see the 0, 0, this is really tiny on this screen, is in the bottom right corner, which means because we are going to be milling this from the underside, that is flipped over, that is mirrored. And also the units are correct. So these are 80 millimeters. If this file didn't open up with the correct units for you, you can go over to options up here, application default, and switch it to millimeters. Or of course, if your CNC machine works in inches, then you can leave it at inches. But I don't think any of the low-end, entry-level wrap 3D printer derived mills actually work in inches. So usually you're going to be wanting to use millimeters here. So we've got our bottom copper opened. Let's open up the drill file as well, the epsilon, that's this one. There we go. And the important thing is to check again that this is lined up. And then we can also open up the profile. You can see it just adds this rim right here. Okay, so let's do the isolation routing on the copper first. So I want to hide all the layers that I don't need. I've just opened drills and profile to check that they are actually lined up. You can either remove these, which I'm going to do, and then reopen them later, or you can also go in here, select, and then plot, remove that. And that's just going to hide it from view, but this list of project files is going to fill up pretty quickly here. So let's get started. Now for isolation routing, which is what I'm going to do here, you just have these 4 options. You have the tool diameter that you're going to be cutting with. I'm going to set this really low because the plan is to use that engraver bit, which isn't going to take away a lot of material. And I want this tool path to be generated even in these tight spaces right here. If you pick a tool that is too large, let's actually try that. Let's use a 1 millimeter tool. You can see that it's not really going to take out any material between the traces and the ground plane here, so it just needs a lot of spacing, which again is something that you can set in Eagle beforehand, but with a large tool it's not going to generate any geometry here. So you want something that is cutting relatively small so it can take out these fine traces here. So if you go to update geometry, you can see now with a 0.2 millimeter assumption of that engraver bit tip, we get complete coverage all the way around our copper tracks. So next up from this geometry, we need to generate our G-code. So jump over here to project, and instead of selecting the Gerber file, select the Gerber ISO file or object or whatever FlatCAM is calling it. And now we get a new set of options. So the defaults here are in inches per some unit, so they're not going to be appropriate if your machine works in millimeters. So the values that I'm going to be using in cut C is -0.1, so it's going to be cutting 0.1 millimeters below our 0 point. Travel Z, that is our safe height, I'm going to set it to 2 millimeters. Feed rate, 300 millimeters per minute is all right. That is 5 millimeters a second, something that every machine should be able to do. The tool diameter here, I don't think actually does anything to the CNC job that we're creating. And basically that is it. We hit generate, and now we have another object, which you can see is rendered in blue. And what I can actually see here is that we are missing some cutout bits between these traces. So I'm going to go back into our Gerber file and recreate the geometry with a slightly smaller bit. I'll be right back. And there we go. I switched the assumed tool diameter to 0.15, and now we get all the areas covered that we want to mill away. And the last step is to export an actual G-code file from the CNC path that we created. So that is super easy. Basically, you just select your ISO CNC object, head over here to the selected one, and export. And I'm just going to save this to a folder on my NAS so I can open it up on my milling computer later. So next up, with the drill files and the outline, it's a pretty similar process. With the drilling job, we get the same sort of options here. The cutting depth, which we want at -2 since we want to cut through an entire PCB. Travel Z, safe height, again 2. Feed rate, 600 millimeters a second should be good. And then because I just want to drill all these holes with the same size drill bit, well, you could use a different drill bit for each of these holes. So for example, there are some 1.499 millimeter holes at the headphone jack. There's some smaller and larger ones in here, but I just want to do all holes with the same bit. I'm lazy like that. I'm just going to select all the drill bit sizes here, and then I'm going to hit generate. So just like before, now we've created this CNC object, and this is not a geometry, this is straight up the CNC job. And again, just like before, export G-code, there we go. Now lastly, the outline, again, select the right Gerber file, head over to selected. Again, we get very similar options as before. The tool diameter, we're going to be using a 0.5 millimeter end mill. You can use whatever size you want. Generate geometry. And one thing I've not figured out yet is why FlatCam doesn't follow this profile but creates just a square box around it. I don't know, it might just be something in my Gerber files that I've exported wrong, but at least we get the correct size of cutout. So same thing as with the isolation routing before. Now we've created that geometry object. We click that, head over to selected, create our cutting depth. So 2 millimeters in depth, 2 millimeters up for the safe travel height, and use whatever feed rate you're comfortable with for your tool. And then we can generate the CNC job, select that, export G-code, and save it out as a G-code file. And that is the CAM processing done. Now we can actually head over to our machine and mill out this board. Now, before I could start milling the actual circuit board, I had to make sure that the bed and the work table on the Sienci CNC was perfectly flat. Now, because the CNC is not the most rigid machine, it's totally possible that the axes get kind of shifted and out of square after moving it. So the first thing I had to do was to mill down this table. That's why there's an MDF sheet on there. That's just a waste plate. And that basically makes sure that it's perfectly aligned to the machine's axes. I put a 6 millimeter end mill in the spindle and just let it flatten the entire bed. And it seems like the spindle on the CNC isn't perfectly square to the rest of the axes and there's no way to adjust it. So it left these ridges on the board that I could either sand off, or in my case what I decided to do instead is to use a scraper and to scrape them flat. That just gives me a cleaner and less fuzzy surface that I can then stick the circuit board to. And yes, this absolutely is the print removal tool that came with the CR10. So with this Makita palm router that I'm using in the CNC, I have to use these collet adapters. Out of the box, it only comes with a 6 and 8 millimeter collet, but the tools that I want to use come with an 1/8 of an inch shaft, which is the most common sort of bit for these smaller sort of CNC routers. This adapter and collet style setup can work pretty well if the adapter and the collet itself are very well made. In this case, well, it's not gonna work out that well, but I'm still gonna try it nonetheless. And because I don't want to start wasting good copper clad raw material, I'm gonna start out with another piece of MDF just taped on top of the bed, just to check that the G-code that I generated out of FlatCam is actually usable and does what I expect it to. So these simpler CNC machines, and in fact even professional CNC mills, are quite a bit more manual to use. And what I mean with that is, for example, you have no end stops for the X, Y, and Z axes. Your host software, in that case Universal G-Code Sender, shows you where your tool is relative to the path you're gonna cut. The X and Y axes are pretty easy to line up because you just need to eyeball it so that your entire cutting path will fit on your workpiece. But the Z axis, and especially in this case, is pretty critical. With this V engraver bit, the deeper we cut, the wider the track is going to be that we remove from the material. So I started adjusting the Z height by using the piece of paper method that you might be used to from setting the nozzle height on a 3D printer, but it's a bit tedious because the engraver bit is so sharp it actually starts digging into the paper. Later on I used a different method that worked better. Now the cut overall looked pretty well and pretty promising, but I noticed that the first few traces were pretty good and took away the right amount of material. The further the machine got into the job, the deeper it would cut. And that to me sounds like a skipping Z-axis where the stepper driver is actually losing steps. Now a quick check with the thermal camera shows that I actually never adjusted these drivers and they were running at, some random current setting. So I dialed them all in to the same reference voltage, in this case 1.05 volts, but again the reference voltage you can measure mean different current values for different driver boards, even if they use the same driver chip. I just set them to some reasonable value where the drivers would get warm, which means they are actually pushing current, but aren't getting that hot that they would be shutting themselves down. And a quick check reveals that the Z-axis actually feels quite a bit better now. So the interesting thing here is that this board isn't just milled with that engraver bit. The isolation routing and the actual traces is done with that V-bit. Then the holes where you actually poke your components through are drilled. And then the outline of the board, so the entire board being cut to size, is done with a regular end mill. And the way that the G-code files are set up means that as long as I don't turn off the stepper drivers and lose positioning that way, I should be able to just swap the tool, adjust the Z height for the new tool, and then just keep on cutting. And that's what I wanted to see with this MDF test piece. And it actually turned out really well. Now for me, the most fascinating part was actually watching the drill bit drill those tiny holes very precisely at exactly the right depth and position. And usually you cut those by hand and they end up all over the place, but with a CNC router drill thing, they just look absolutely perfect, and they were. Okay, so with the test piece done, it was time to move on to milling some actual copper clad. Because I'm using these larger cutoff bits of copper clad board, I couldn't just tape them down to the base bed of the machine because they would be physically too large and would collide with these edges of the wasteboard that I couldn't mill flat. So instead, I just taped it on top of that piece of MDF that we just cut, and that also gives me a reference because we already have all the cuts to where the finished board is going to be. So to secure the copper clad, I used the same method as before, which is just a few strips of this 3M carpet adhesive double-sided sticky tape basically. This holds it down really well and is easy to peel off once it's done, with a bit of heat if necessary. Now to set the Z height for all my tools, I used a bit of a different method this time, and I'm actually liking it way better. Instead of using a shim or a piece of paper to gauge that point where the tool is just touching your workpiece, I instead left the collet on the spindle open, which means it's just grabbing down hard enough so that the tool doesn't slide out, but it's still loose enough so that I can just use the Z-axis and drive the tool into my workpiece, and the tool is just going to slide up in that collet, and in that position my Z height is set perfectly and I can just lock down the collet like usual. I gotta say, this works incredibly well. So the first tool I loaded up like this is the 0.8mm drill bit. I used this to drill out all the holes to give me a visual representation of how well my actual isolation cut is going to come out. And then I moved on to loading the engraver bit to cut the actual circuits. So yeah, that is a bit of a fail, and it's not like I didn't quite expect this. I mean, the main problem here, wow, tape is actually sticking down pretty well. The main problem here is that the traces I'm cutting are too wide, and that's 2 or 3 things that I can trace that back to. The first one would be that the collet I'm using in this palm router, because it is a wood router at its core, and I'm using these adapter collets that kind of look like this. So you're stacking tolerances essentially. The original collet is going to have some wobble to it. These are going to have some wobble to it. And if you're using an engraver tip like this that has just a really, really fine tip, any sort of amount that this kind of wobbles around while it's spinning is just going to make your cut wider. The other problem I'm also seeing is that these break. The tip on these is relatively sharp. It does have a bit of a radius on it, but it still breaks super easily. And again, that is just something that I would blame on this overall setup, because again, it's not running round, so it's not cutting exactly the way it's supposed to. And also, I mean, yeah, these are just super fragile, so unless you have a super perfect setup, you can't really expect them to last all that long. And the last thing, I guess, is just mechanics in this entire setup. So the CNC is using lead screws for all 3 axes, so these by nature have a bit of slop in them. It does use like spring-loaded anti-backlash collars, but it's not perfect perfectly accurate. It's not ball screws that would have no slop at all. So it's not an absolutely precise system. So because this just isn't usable, I'm not getting the traces that I need. This is supposed to be a trace, but it's pretty much all gone. I'm not getting all the traces out of it. And, you know, some of the traces on this board are just what I'd consider optional functionality. I made a quick new revision of this board that cuts out those traces, which, because this is a single-sided board, is going to allow me to use wider traces that won't have to pass between solder pads, which, you know, is something that is tricky to mill out either way. So with a more simplified board, I can just use super wide traces and spacings. And with that new layout, I don't think, even with these shortcomings, that's going to be a problem. And with that loaded up, I'm going to move this board over just by a bit so that we get a fresh area where there's no drilled holes in there yet. And yeah, we're just going to try the same thing again. Okay, no, look at that. That's just not working out. I don't know if the engraver bit is just wearing out or whatever. I'm not a fan of the engraver for copper. Instead, what I'm gonna try are these 0.5 millimeter end mills, I guess. These are made for PCB milling, but I think it's more like outline milling and not copper isolation milling, which is what we're doing here. Still, I compared the size of the 0.5 millimeter tip of the 0.5 millimeter cutting edge here to the trace width we're already getting, and it is looking like the isolation trace we're cutting is already at 0.5 millimeters, so we don't have much to lose. I'm gonna keep the machine in this position and just mill over the existing isolation traces again. And the good thing is with these end mills, because they don't have that taper to it, it doesn't matter as much how far you actually cut into the material, because the trace you're cutting isn't gonna get wider or thinner, as opposed to, you know, something like this is already a pretty pointy and steep one, but if you get your height off, your width is also going to be different. With this case, because it's just a straight end, doesn't matter. Holy moly, what a champion. That 0.5 millimeter bit, wow, that was flying through that PCB. Well, it's not a, is it a PCB? Is it an MCB now, a milled circuit board? Alright, so I just gave this a quick sanding with some 800 grit sandpaper to get rid of some of the raised edges where the milling bit cut through. And, you know, let's look at this PCB and just go through what worked and what didn't. And the first thing obviously is those raised edges that I just talked about. Because I was using the milling cutter here instead of the engraving bits, you know, these milling heads have a spiral flute to them. These just cut straight. So naturally, when this thing is turning, when this bit is turning, it will want to pull material up. Instead, these will just want to push it out sideways. So naturally, using an actual end mill, an actual cutter like that, will want to pull that thin copper film. This is just 0.035 millimeters, so 35 micron thick copper. It will want to pull it up, and it gives you quite sharp edges. In fact, there's still some around these corners here. While the engraving bits generally tend to cut a bit more cleanly, and these end mills just need to be super sharp to give you a super clean result. Now, the second thing that I still don't think is perfect is that the trace width that this thing has cut out is wider than the actual bit. It's not actually by that much. Looking at the G-code, this isolation width should have been just the width of this end mill, and especially with the engraver bit that has a tip that goes almost to zero. This should have been way thinner. Let me see what the engraver looks like. Yeah, it's a bit thinner, but it's not by much. It is still way thicker than what this tip would be capable of. Now that to me just confirms that this collet, this is the one that the Makita router comes with, and the combination with this reducing collet do add up in tolerance, and the end mill or bit or whatever you're using in this doesn't just turn smoothly, but actually wobbles around as it turns. And that just naturally creates a larger cutting area than, you know, what these tools are designed for. And with that, I think the idea of having traces run between these pads is just not feasible or not reliable. You can see some of the copper areas between them are still there, but for example, back here, it's already starting to fade away. Now, another area I kind of want to point out to you is this area up here, and you can see these traces are not the same width. These are designed to be the same width, but this one is more than twice as wide as this guy. And I think the reason for that is this side of the cut right here comes inwards from this pad, while this side is actually just flush. So up here, the cutter should have moved a bit inwards, which it couldn't. Up there, it didn't even make that attempt. So that tells me that there is some backlash happening in, what is this, the x-axis. And as far as I can tell, if it's happening on the x-axis, it's also going to be happening on the y-axis because they're built very similarly. And that is just a combination of the Sienci CNC using the stepper motors, lead screws, well, backlash reducers that it does. And overall, the motion system on the Sienci CNC is just not made for these high precision, intricate parts. You can see the backlash or the deviation in the dimensions adds up to at least 0.5 millimeter between these two. And that is just something that is going to be very noticeable, not just in PCB milling, but also in making, you know, aluminum parts. If the dimensions of an aluminum part are 0.5 millimeter off, you will notice it, especially when two parts have to mate together. It's going to make a noticeable difference. Up here at these pads, this is the programming header. You can see that the pads are kind of missing. There is supposed to be a copper ring around each hole that was drilled, and you can see it. And this one looks good. This one is half there. The one with the trace, thankfully, is still there. But for example, this guy right here is completely missing in action. I did already use a smaller drill bit than this was designed for. This is a 0.8. This is designed for 1 millimeter drilled holes. So again, if this thing wobbles, it's going to drill larger holes, but also the isolation contour around it is going to be larger and is going to take away more copper. But I think with these modifications to the PCB to make it a bit simpler and a bit more machinable, manufacturable on the Sienci CNC, this is still very usable and it should still fit all the parts I want to put on it. So let's get this thing sorted up and see if it actually works. So yesterday I asked on Twitter about what people think these milled circuit boards should be called, and we got responses from everything from MCB for milled circuit board to ICB for isolation routed circuit boards to calling them Steve, which I think is the most likable version of these. And obviously with this milling process, there is no solder resist on this board. So while on a board like this, all the green stuff you see is actually a coating that prevents the solder sticking to all the places you don't want it sticking to. Here with this milled board, we don't have that. So it's super easy to get these bridges of solder that go past where your pad is and short out to, in this case, a ground plane or adjacent pads. So you just gotta be really careful soldering these things and make sure you don't short out like that. And while I'm soldering up the rest of this board here, I want to say a special thanks to all my patrons who are making this channel possible. In the shoutout here this month are Luke Ingemann, Francisco Peebles, Paul Arden, Phyllis Struder, Christopher Day, Andy Fair, Marek Serra, Brian Raker, Dexter Gillette, Jonathan Mullen, James C. Foley, Mike McGee, Marcus Harms, Robert Hornbach, Nathan Hast, and Dorian Gray. If I've butchered any of your names, please let me know, send your message and I'll try to do better next time. But again, thank you so much for all your support. I appreciate each and every one of you who are helping fund this channel. You guys are awesome. And if you're considering joining in as well, head over to tom3d.org/Patreon for more info. Okay, so that is the board completed and all assembled. You can see I've plugged everything in. Everything is routed out and working and functional, and we're gonna get to what this actually does in a second. But you can see a few changes that I've made. There are two yellow wires that I've soldered in. The first one is this one right here. This is a trace that I simply forgot to include in the routing in the actual PCB making process in Eagle. I never noticed that this wasn't connected, so I just had to jumper it. Also, there is a second jumper wire here that connects these two ground planes. They are electrically connected, but it would have to go all the way around here and through here, so I just wanted a more direct connection. This is just one of the things with a single-sided PCB. You want a ground plane on pretty much any design. In this case, it protects against humming and other sort of noise that would get coupled into the board. But because we have a single trace running through this ground plane, this gets split up. In a two-sided PCB, you would have ground planes on either side, and that wouldn't be an issue. So I just connected these up right there. But electrically, this thing is working perfectly. There are no solder bridges, there are no shorts, there are no copper bits that stick out and short stuff out. This thing is working perfectly, and that, I think, is the entire point. So what does it actually do? This is a DSP amplifier kind of application board, I guess. It has this board with an audio DSP on it. We have I think there's a 10-watt amplifier, plugins for speaker out, power in, audio in. It has a headphone jack right here. We can plug in the programmer for the DSP. You know, really neat and compact solution. So what that actually does is we can influence the way a speaker sounds quite a lot. Now, this is a $2 3D printed speaker, and you know, without anything, this thing sounds pretty bad. I mean, this is basically what pretty much any Bluetooth speaker sounds like without any audio processing applied to it. So if you enable the DSP right here and add our equalizer and limiter and all that, there we go. Much better. It's not perfect yet. This thing still needs a lot of optimization, but it is a lot better. And you know, if I eventually build this out to a full DIY Bluetooth speaker, then this is exactly what it needs and exactly what's going to make this thing sound, I don't know if it's going to sound great, but it's going to sound very acceptable. Okay, so what would I do differently with routing this PCB? First off, I think the result is great. It's usable, it's functional, it does what it needs to do. So that is a full success on that front. However, for the more detailed version, which is this engraver bit version that I first tried out, this machine is just not the right tool, and that has a few reasons. I've already talked about backlash, I've already talked about runout and wobble on the bit. Those two things certainly limit what the Sienci can do. On top of that, if you really crank this Makita spindle to the max at 30,000 RPM, I think it does, the entire thing just starts vibrating and shaking. So I think this tool on this is just not great because it's heavy and the motors have a hard time. So I think what we should be using instead is one of these ER11 spindles. This is a brushless version. Even though it looks kind of janky, the runout on these is actually very good, and it's a lot lighter than the Makita tool. Doesn't spin quite as fast, but I think it's just more suitable for this sort of setup. And it has the ER11 collet right in there, so you can chuck up the 1/8" tools perfectly without any need for adapters. But of course, with the parts that are already on the CNC, we can make PCBs. It's just a bit limited to what they can actually have in them. So first of all, you need chunky traces. You need like super wide traces relative to what's usually used. The idea of routing traces between pads, so between these solder joints, you can usually have a trace go between them. It's just not really possible with this setup. And basically you just need to set up your Eagle design file or your PCB design file to have large gaps, large isolations, large traces, just everything a bit larger and a bit chunkier. But still, our standard grid for components here is 1/10 of an inch, so 2.54 millimeters, which is, you know, something that we can very easily do on this machine, and I guess on any other CNC machine. That's not something that needs super high precision. It's just something that you know, is usually not done on PCB manufacturing because we can do so much better, and it just makes our lives easier if we can do more intricate designs like this. But yeah, overall, I am very happy with how this turned out. I'm very happy that I can start making some custom PCBs now without, you know, having to order them and wait for a few weeks for the parts to get here, or having to go through an etching process, or using toner transfer, or, you know, using chemicals. This is just a purely mechanical process. I think it's very usable. It turned out very well. I'm still going to try to make PCBs with a 3D printer in an upcoming video. That is going to involve etching, but it should allow us to make some more intricate designs, at least I hope. So stay tuned for that. If you want to make the same sort of PCB that I have, or if you're just interested in the components that I used, I'm going to be linking those below, both the DSP board, the amplifiers, and my board design itself. You can download that freely, no copyright applied to that. Make your own if you want to, or use it for your own projects in some other way. Anyways, if you enjoyed the process, give the video a thumbs up, get subscribed if you want to see more like it, and you can support the channel through YouTube memberships or Patreon or other means. That is all linked below. Thank you for watching, and I will see you in the next one.